Hi everyone and welcome back to Matthew Wester. Today I'm going to explain the pH scale, how it relates to acids and bases, and the two major acid-base theories that we'll be using in chemistry for the Regents. So to start off, the pH scale measures how acidic or how basic a solution is. So the typical scale is ranging from 0 to 14, and in the middle we have 7. So a pH of 7 is considered neutral. So I'm going to mark that as neutral in green. And a pH of 7 means that the solution is neither acidic nor basic. An example is pure water. But a pH below 7 indicates that the solution is acidic. So the lower the pH, the more acidic a solution is. But if you have a pH above 7, it indicates it's a basic solution. So the higher the pH, the more basic the solution is. So I'm going to mark it as more acidic, and then here it's more basic. Now, the pH of a solution depends on the concentration of hydronium ions. So hydronium ions is marked like this, H3O+. That is the concentration of hydronium ions. So more hydronium ions means that you have a lower pH and a more acidic solution, but fewer hydronium ions means you have a higher pH and a more basic solution. So if I were to write this, the more acidic, the more H3O+, but the more basic, the less H3O+. Now, there is a mathematical relationship between pH and hydronium concentration, and we represent that by pH is equal to negative log and the concentration of hydronium ions. So what this relationship is showing is that the pH depends on the hydronium ions. So when you change the concentration of hydronium ions, you're impacting the pH. So just as one example, if we increase our concentration of hydronium ions, the pH is going to decrease because we know we associate that with more hydronium ions, and therefore the solution is more acidic. Now there's another way to determine acids and bases, specifically through the Arrhenius theory of acids and bases. So according to the Arrhenius theory of acid and bases, an acid is a substance that increases the concentration of H+ ions or hydronium ions, which is the same thing as H3O+, and a base, an Arrhenius base, is a substance that increases the concentration of OH- ions, which is hydroxide ions. And both of these happen in water. So for example, if we have a solution that's undergoing a chemical reaction and it releases hydronium ions, that means that the solution is more acidic because we're releasing. So if we're releasing H+ ions, the substance or the solution is becoming more acidic. But if we're releasing OH- ions, the solution is becoming more basic. Lastly, another theory is the Bronsted and Lowry theory that states that an acid is a proton donor and a base is a proton acceptor. So I'm just going to write that over here. The acid donates a proton, which is also just H+, and the base accepts the proton. So overall, just as background, you should know that the pH, again, is determined by the concentration of hydronium ions. The pH of a solution decreases as there's an increase in hydronium ions, and the pH of a solution increases as the concentration of hydronium ions decreases. And an acid is what increases the concentration of H+ or hydronium ions in water, and a base is what increases the concentration of hydroxide or OH- ions in water. And that an acid donates a proton H+ and a base accepts the proton H+. So now let's actually get into the reading. Optimal blueberry growth occurs within an acidic soil pH range of 4.5 to 5.0. A blueberry farmer had the soil from a local field tested to plan for the upcoming planting season. The diagnostic results indicate that the soil currently has a hydronium ion concentration of 1.0 times 10 to the power of -8. Figure 1 shows indicators that could be used by the laboratory to test agricultural soil pH. One way farmers can optimize alkaline solution for specific crops like blueberries is by adding elemental sulfur. Equation 1 shows the multi-step biochemical process when specialized bacteria in the soil oxidize elemental sulfur, altering the local hydronium ion concentration. So here we have the equation. We can see that sulfur is being added, and that in the products we see that hydronium ions are being produced. So let's just keep that in mind. Now here we have our indicators, we have our pH range. So if you want to know how to read this pH range, the number on the left indicates the more acidic side of the range, so it would be yellow, and the number on the right side indicates the more basic side of that range, so it's going to be red. So there's a transition in color. Now let's look at the question. Based on the initial soil diagnostic test, what is the exact pH value of the farmer's field before any chemical treatment is applied? Well, it's asking for the exact pH value. So it tells us that the soil currently has a hydronium ion concentration of 1.0 times 10 to the power of negative 8. So I'm just going to write that, 1.0 times 10 to the power of negative 8. So this right here represents our concentration of hydronium ions, which is also written as this. So if we look back at our equation here that I had written here, the pH equals negative log, and then the concentration of H3O plus ions, I'm just going to put this here because we're going to use that. Now there are two ways you can do it. I'm going to show you this way, and then I will show you the easier way. So if we put this in our calculator, we can input this as this here because that's our concentration of hydronium ions, and then we just see what our answer is. So if we input in the calculator negative log and then 1.0 times 10 to the power of negative 8, we're going to get an answer of 8. And this answer indicates that the pH is equal to 8. But a quicker way you can do this that only applies when this first number here is 1.0 is that if we look at the exponent here, if we take just the x value, so if we just take 8, right, that is our pH. So our pH regardless is 8. The second question, which two indicators from figure 1 when used independently on different samples of treated soil would provide results that together are suitable for confirming that the soil pH has reached the optimal range of 4.5 to 5.0. So the range that we want is 4.5 to 5.0. So it's asking basically, these are our ranges, right? These are our different indicators, and they all have their own individual ranges. But if we put them together, which range would be most useful in order to help us find this specific range? So let's look at our first option. We have Alzarine yellow and Bromcresol purple. So we have these two. We can see that the pH for Alzarine yellow in the lower end is 10.2, and then for Bromcresol purple, the upper end is 6.8. So if we rewrite the range that we do want, which is between 4.5 and 5, this range would not be suitable because it's too broad. It's too big of a range, so it's going to be harder to narrow it down. So this one won't work because, again, 10.2, way off. So it won't be that one. Now, I want to work around before we get to the actual answer. So let's do methyl red and Alzarine yellow. So methyl red and Alzarine yellow. So now we're left with Bromcresol purple and Brompheno blue and Congo red. So before we start comparing these two options, a quick tip for these types of questions is that you want to look for an indicator whose range is just below the target pH and one indicator whose range is just above the pH. So we want something that's above and below, somewhere between there, because that way we have a range that's going to help us narrow down the actual range that we want, the actual pH range that we want. So if we look first between Congo red and Brompheno blue, we can see that they both start at 3.0. Now the main problem with these two indicators is that this range here, 3.0 to 5.0, overlaps with this one. So it's not that useful when it comes to narrowing down our options. Now, even though 4.5 does fall below 4.6 and 5 falls right around the range, the matter at hand is not that these numbers have to fall directly inside the range, but that we need a clear upper and lower boundary, so above and below. And since the range from 3.0 all the way to 5.0 is too broad, it's not going to be very useful when it comes to narrowing down the value of 4.5. Because all this is going to tell us is that the pH has to fall somewhere below 5.0, but it also falls somewhere below 4.6. And that's not very useful. We want something that tells us something is above 4.5 at least. But before we make our final decision, let's look at the range or the indicators Brahm Crystal Purple and Brahm Pheno Blue. So if we look at Brahm Crystal Purple, it's between 5.2 and 6.8. Now what this range is going to tell us is that the pH has to fall below 5.2 because 4.5 and 5 fall below 5.2. But now if we look at the range of Brahm Pheno Blue, which is 3.0 to 4.6, it's going to tell us that the range has to fall somewhere above 4.6. So the pH is about 4.6 or higher. Because whenever we say above 4.6, we're taking into account the 5. But when we say below 5.2, we're taking into account both of the values. So it's like an upper and lower boundary. So if we were to write this together, we would say 4.6 is less than the pH, but it's also less than 5.2. So that means that the pH has to fall between 4.6 and between 5.2. So it's going to look like this. Even though 4.5 somewhere falls right before 4.6, we still know that Brahm Pheno Blue is going to end right around the target pH. And we know that Brahm Crystal Purple is going to begin at 5.2, which is just above the target pH. So whenever you're doing these types of questions, you usually want a pair that brackets or takes into account the desired range from both sides. And when you're looking at both options between B and C, B does a better job at that than C. Because C, again, is too vague and it doesn't really take into account the upper and lower boundaries. So our answer is going to be B. Next question. Circle the row in the table below that completes the scientific claim describing the correct cause and effect relationship of adding elemental sulfur to the farmer's soil based on equation 1. So if we look at the column, we see that we have 4 different causes. We have a cause that either increases or decreases the pH, or one that decreases or increases the concentration of hydronium ions. Well, if we remember, the concentration of hydronium ions is what impacts the pH. So we can immediately eliminate 1 and 3 because the pH is not what's affecting the hydronium ion concentration, it's the hydronium ion concentration that's affecting the pH. If we look back at the equation, we can see that hydronium ions are being produced, they're being released. So we're increasing hydronium ions. So that means that we can eliminate 2 because we're not decreasing the hydronium ion concentration, we're increasing it. Now, if you want to fact check this, if we increase the hydronium ion concentration, we know that the pH is going to decrease because the hydronium ion concentration is associated with acidity. So the solution is going to become more acidic. And since it's by 1,000, we know that the pH scale goes logarithmically. So if we do 10 to the power of 3, which is right there, it's going to be equal to 1,000. Let's look at the next question. A student claims that adding elemental sulfur will make the soil environment more basic because it produces a polyatomic ion. Well, if we look at the equation itself, we can see that we're actually releasing hydronium ions. And when we're releasing hydronium ions, that's associated with an acidic solution, according to Arrhenius acid. So I'm going to refute the student's claim because in equation 1, there was H3O plus ions being released. meaning the concentration of hydronium ions was increasing, therefore increasing the acidity of the solution. Next question. Determine the factor by which the hydronium ion concentration must change to shift the farmer's initial soil from its original pH to a target pH value of 5. Well, we know from the first question that the initial pH was 8, and our target pH now is 5. So that means that the pH is decreasing, so it's becoming more acidic. So that means the concentration of hydronium ions is going to have to increase. But now you have to figure out by how much. Well, we know that the pH scale moves logarithmically, so it's by tens, the power of tens. So I'm going to draw it out. We have our scale. Let's just say 5 falls here, and then 8 is over here. If our initial pH is 8 and our goal is now 5, we're going to have to move 1, 2, 3 times. So that means 10 to the power of 1, 10 to the power of 2, and then 10 to the power of 3. So 10 to the power of 3 is 1,000. So that means that we're going to have to increase the concentration of hydronium ions by 1,000. Next question. The chemical adjustment of agricultural soil requires precise monitoring, as over-acidification can damage crop root structures. Using ammonium-based fertilizers such as ammonium sulfate provides a more controlled alternative that reduces the risk of sudden severe drops in pH. The equations below demonstrate 2 pathways by which dissolved ammonium ions can contribute to gradual soil acidification. Identify the acid and the base in the forward reaction of equation 2 according to the Bronsted-Lowry conceptual definition. Well, if we remember from our previous notes above, that an acid is the proton donor and a base is a proton acceptor. So if we look at equation 2, which compound is losing a proton and which one is gaining? Well, let's look at NH4. NH4 turns into NH3. So it's losing a proton. It's losing an H plus ion. And then we can see that H2O is gaining an H plus ion because then it becomes H3O plus. So in this case, according to the Bronsted-Lowry conceptual definition, NH4 is the acid and H2O is our base. So since NH4 becomes NH3 and H2O becomes H3O plus, NH4 is the acid donating an H plus ion and H2O is the acceptor. Describe the similarities and differences in how the products of equation 2 and equation 3 affect the bulk pH of the soil mixture. Well, if we look at then equation 3, we can see that 2H plus is being produced. And H plus is the same thing as hydronium ions, which is the same thing that we see in equation 2, H3O plus. So in both equations, hydronium ions are being produced. So the solution is becoming more acidic. So the pH is decreasing. However, a difference is that equation 2 is equilibrium reaction because of these 2 arrows, meaning that it can go forward and backward. So the production of hydronium is limited. But equation 3, it has a single arrow, so it produces H plus ion completely and consistently. It doesn't go back and forth. So even though both equations produce hydronium ions, increasing the acidity of the solution, equation 2 is an equilibrium reaction, while equation 3 proceeds to completion and produces hydronium ions directly.